Hey stats, welcome back. Let's talk about significance tests. So in a significance test, we are looking to see if there is a difference between the two populations or two proportions that is big enough that would say that there actually is a difference, or, of course, could it be due to random sampling? Because, as we know, if you take two samples, they will very likely not be exactly the same. So it's possible that you would get a difference in two samples, but the question, of course, is it big enough that it means that there's actually a difference in the populations, or was it just due to random sampling? In a significance test about the difference between two proportions, our null hypothesis is always going to be that there is no difference in the proportions. Or, in symbols, P1 is equal to P2, or really, because we're talking about the difference, P1 minus P2 is equal to 0. This is always going to be our null, that there is no difference. Our alternate then is going to be whatever difference we think is happening. Our alternate hypothesis, whatever difference you expect. So that could be a bunch of different things. That could be that P1 is greater than P2, or P1 is less than P2, or P1 is not equal to P2. Of course, we would change those all to be differences. So P1 minus P2 is positive, P1 minus P2 is negative, or P1 minus P2 is simply not equal to 0. These are going to be our possible alternate hypotheses. And this leads us to the two-sample z-test for the difference between two proportions. Suppose the random, normal, and independent conditions are met. These are going to be the same as the confidence interval, so I'm not going to go through those. But if those two things are met, you're going to do everything we've talked about for a significance test. We are going to create a null and an alternate hypotheses. We're going to check our conditions, and then we need to calculate a test statistic. Remember, a test statistic tells us how far from the parameter our statistic is. So in general, it's the statistic minus the parameter divided by the standard deviation of our statistic. In the case of a two-sample z-test for the difference between two proportions, our null hypothesis, if you recall, is always going to be P1 minus P2 is equal to 0. Our parameter is always going to be that the difference is 0. So this piece, the parameter, is going to end up not being included because it's just 0. Our statistic is going to be the difference between our two statistics, or p hat 1 minus p hat 2, and the standard deviation of our statistic is where things get a little bit interesting. We know that this is sigma sub p hat 1 minus p hat 2, which is the square root of p1 times 1 minus p1 all over n1 plus p2 times 1 minus p2 all over n2. However, the big assumption we make with the significance test is that the null hypothesis is true. We assume our null hypothesis is true to show that it's not, or to show that we can't prove that it's not. And so if our null hypothesis is true, let's consider what that means. If our null hypothesis is true, that means P1 is equal to P2, or we are sampling from the same population. This is working under this assumption. This might not necessarily be true, but we need to kind of essentially pretend it is. And if that's true, then we need to calculate something that is called a pooled proportion, otherwise known as a combined proportion. Because of this, we need to calculate pooled proportion, sometimes known as combined. Oops. What is a pooled proportion? Well, P hat C is going to be a combination of our statistics. So if we think about it, P hat 1 is x1 over n1. P hat 2 is x2 over n2. If our assumption again is that we are sampling from the same population, then these two samples need to be combined to make up this pooled proportion, which is x1 plus x2 over n1 plus n2. They use C again because it's combined. Your textbook says pooled, so I'm going to use both languages so we know. This then is actually the thing we are going to substitute in for our standard deviation, which means my final formula for the test statistic would be Z is equal to, remember it's statistic, P hat 1 minus P hat 2 minus parameter, well our parameter is 0, so I'm subtracting 0, all over that standard deviation, which is made up of, in this case, our pooled proportion. P hat C times 1 minus P hat C all over n1 plus P hat C times 1 minus P hat C all over n2. This is our test statistic. It tells us how far from our parameter our statistic is. Once we find a test statistic, of course, then we calculate a p-value, or the probability of our test statistic happening, or more extreme, in the direction of our alternate. So we're going to find the probability that Z is less than whatever that test stat is, or we're going to find the probability that Z is greater than whatever that test statistic is, or the probability that Z is not equal to our test statistic. And as I just said, but I will say again, this symbol is based on our alternate hypothesis in the direction of the alternate. And once we calculate a p-value, our conclusion remains the same. If our p-value is less than our significance level, we are going to reject our null. And if our p-value is greater than our significance level, we fail to reject. So honestly, the only thing that is different is that in this in this significance test, because our assumption is that our two samples came from the same population, we are assuming the null is true, that the populations are the same. We need to combine them to calculate this standard deviation. Let's look at an example. Are teenagers going deaf? In a study of 3,000 randomly selected teens in the 80s and 90s, 15% showed some hearing loss. In a similar study of 1,800 teens in the 2000s, 19.5% showed some hearing loss. Of course, those are different numbers. 15 is not the same as 19. However, the question is that different enough that we can say there is a difference in hearing loss? Or is that we just grabbed a sample from a different part of the country who had more hearing loss? Do these data give convincing evidence that the proportion of all teens with hearing loss has increased? And then, of course, we'll answer B in a moment. I wrote out the work for this so that it didn't take my handwriting. So, of course, as we go through, if you need to pause the video to write things down, please do. In our state, we need to say the significance level and the hypotheses. So let's think about it. Our null we know is going to be that there is no difference, that P1 minus P2 is 0. Our alternate, what are they asking us to find? We are looking for evidence that the proportion of all teens has increased. I am going to say the 80s and 90s is P1, and the 2005-2006 is going to be P2. That means if P1 minus P2 is what we are trying to find, and we want to see if the difference has increased, that would mean P2 is greater than P1, or that their difference would be negative, right? If the 80s is less than in the 2000s, then the 80s minus the 2000s is going to be a negative number. That means our state would look something like this. we would like to test the following hypotheses at a 5% significance level. Our null hypothesis is that P1 minus P2 is 0, and our alternate is that P1 minus P2 is less than 0, is negative, where P1 is the true proportion of teens with hearing loss in the 80s, and P2 is the true proportion of teens with hearing loss in 2005 to 2006. Once we have our state, what we are trying to find, we get to figure out our plan. In our plan, we are going to use the two-sample z-test for the difference in population proportion, assuming random, normal, and independent. Random, they were both randomly selected samples, so we're good to go there. Normal, we check our n times p hat for both populations. All of those numbers are greater than or equal to 10. And independent, there are more than 30,000 teens in the 80s and 1,800 teens in the 2000s. Main thing to note here, two-sample z-test for the difference in proportion. Checking our plan, checking our conditions in our plan, we're good to go for the do, and this is the piece that I want to study or look at a little bit more. In our do, we need to calculate our test statistic, or statistic minus parameter, our parameter being 0, all over the standard deviation. Now, we need to calculate this pooled proportion, which is going to be this work right here. P hat 1 was the 1980s. So we're looking at the 450 out of 30,000. Just kidding, 3,000, which was that 15%. And P hat 2 was the 351 out of, 351 out of 1,800, or that 19.5%. So our pooled proportion, adding those together, 450 out of 351, 450 plus 351, oh my goodness, over 3,000 plus 1,800 would give us a pooled proportion of 0.167. This work showing this is important. This work showing what our test statistic is important. However, we can calculate these things in our calculators. Let's do that now. If I go to my, again, stat and over to tests, here I want the two proportion z-test, option 6, where our x1 is the 450 out of 3,000, our x2 is the 351 out of 1,800. Our alternate was that P1 is less than P2, and we are going to calculate. I'm going to drag this in so we can analyze all those numbers, because there's a lot of information that we are given, and I want to make sure we know what it is. So if we see, we are given that our z test statistic is negative 4.04, which I had calculated here as well. So then we're finding the probability that z is less than that thing because of our alternate hypothesis. And look at our p-value. P is equal to 2.58 times 10 to the negative 5. 2.58 times 10 to the negative 5, or 0.1234258. That is about 0%. If you ever see a p-value that is a decimal, a whole number and a decimal, you need to notice that there is probably a times 10 to the something at the end. Our p-value is almost 0. What does that mean then for our conclusion? Well, our p-value is less than alpha. We are going to reject our null hypothesis, meaning we do have convincing evidence to say that the true proportion of teens with hearing loss has indeed increased. B asked us a really important question. B says, between the two studies, Apple introduced the iPod. If the results of the test are statistically significant, which they are because we rejected the null, Can we blame iPods for the increased hearing loss in teens? So we did see a statistically significant result. We saw that teens in the 2000s had more hearing loss than teens in the 1980s and 90s. However, can we conclude that this is strictly because of the iPod? And the answer to that is no. We do not know how these teens lost their hearing or had an issue with that, because we were not told anything about the way that this study was conducted. It was not a cause and effect. They did not test iPods here. We cannot conclude that iPods are the sole cause. It is possible that they impacted in some way, but we cannot conclude that iPods are the sole cause of this, oh my goodness, sorry, of this hearing loss. Why not? Because this study didn't give us any sort of cause and effect in the information. If you have questions, please send me a message. Otherwise, good luck with the homework.